Okay, so we talked a lot about enzymes so far, but now we're going to talk about enzyme inhibitors. And these have huge impact on health because we need enzymes for everything that we do in our cells. So if we have inhibitors present, what inhibitors do is block the enzymes from action. And so we're going to talk about 3 different types of these: uncompetitive, competitive, and mixed, and how those affect the Kcat, the Km, and the catalytic efficiency. So you're also going to be able to interpret Lineweaver-Burke plots or Michaelis-Menten plots to determine the type of inhibition. You're also going to predict which molecules would likely be uncompetitive or competitive inhibitors. So first off, I'm going to explain the plot in front of you. This is what's called a Lineweaver-Burke plot. Lineweaver-Burke looked at those hyperbolic plots for the Michaelis-Menten plots and was like, oh no, we can do this so much better. This is also called a double reciprocal plot. Blah. Double reciprocal plot. Because all Lineweaver-Burke did, if you remember back to the Michaelis-Menten plot, what we plotted was the concentration of S versus the velocity, the initial velocity of the reaction. So what we did here is we took 1 over concentration of S for the x-axis, so 1 over this, 1 over the velocity, 1 over the initial velocity here, for the y-axis, so that's why it's the double reciprocal plot. And when you do this to a hyperbolic plot, you get a straight line. And on the Lineweaver-Burke plot, this is wonderful, you're going to love it. The y-axis, remember the y-axis is related to velocity, right? So the velocity that we care about and that we can calculate from plots is the Vmax. So, this being reciprocal, this y-axis is equal to 1 over Vmax. Similarly, the x-axis, remember the x-axis units are 1 over S, so the S constant that we know that involves molar would be the Km. So this, being on the negative part of this plot, we have to take the reverse of that. Negative 1 over the Km is the x-axis. So we have a really great way to get quantitative measures of the Vmax and the Km. And then of course we can calculate the Kcat based on the Vmax by dividing the Vmax by the concentration of enzyme. Boom! Boomski, right? Absolutely lovely. Additionally, the slope of this line is equal to the Km over the Vmax. Okay. So, remember the equation for a line. Y equals mx plus b. So we know that this value is going to be the Vmax, and the value for m is the Km over the Vmax. So without even doing too much math, we know the Vmax, 1 over the Vmax, and we can figure out Km based on those values. Okay, so Lineweaver-Burke really has it going on. This is a really quantitative way to measure the Vmax and the Km without having to guess with that little, with the dotting line. You're like, oh, maybe it's here. This is quantitative. We love Lineweaver-Burke. Okay, so it's really useful to use Lineweaver-Burke when we're talking about inhibitors. So the first inhibitor I want to talk about is the most, well, what I feel is the most intuitive, and that's competitive inhibition. So in competitive inhibition, the inhibitor, I, competes with the substrate S for the active site. So what that looks like in terms of the equation that we've been working with, enzyme plus substrate makes the enzyme-substrate complex, makes enzyme plus product. So this enzyme combined the substrate, or it combined the inhibitor to make, I'm running out of room here, to make the enzyme inhibitor complex. One thing I want to mention is that the inhibitors that I'm talking about today are reversible. Most inhibitors are. These only make non-covalent bonds. These can be released. Non-covalent bonds. There are irreversible inhibitors, and as you can imagine, those would make covalent bonds. So those are sometimes called suicide substrates, where they dive into the active site, they make covalent bonds, and then they're stuck there for infinity, right? So those substrates can never be released, so that's why it's called the suicide substrate. They go in and basically inactivate the enzyme by also inactivating themselves. Okay, so remember back that the K-cat is this arrow, right? And so this is K1, this is K-1 for these two reversible arrows. So as we can see, the competitive inhibitor will likely look like the substrate because it's binding the enzyme's active site. So that's how you can tell it's competitive. So this inhibitor does not affect the K-cat. It only affects the Km. Therefore, it will have the same K-cat, the same y-axis value. However, the Km will likely increase. And so what that means, I'm trying to make this line straight, when we add in the inhibitor, we see the line shift upward. We see the value for Km is, so this is the -1 over Km. This is now a worse Km because this Km is a higher number. K-cat stays the same. Because the enzyme's only binding here, so it's only affecting this part of the reaction. Doesn't affect the K-cat at all. Okay. Next one we're going to talk about is the uncompetitive. So what the uncompetitive does is this will bind the enzyme substrate complex. It does not bind the enzyme alone. It only binds after the substrate has bound. So here's where the inhibitor will bind, making enzyme inhibitor substrate complex. I always write it this way, EIS, because this is the German word for ice cream. It amuses me. Ice. Okay, anyway. So, because the inhibitor is binding here, you can imagine it has an effect on K1, K-1, and K-cat. And you're absolutely going to love what happens here. So, it makes the resulting Lineweaver-Burke is a parallel line. I'm doing my best to make this look parallel. Okay. So when we add the inhibitor, we see the line shift up, and we see changes to the K-cat and to the Km, or sorry, to the Vmax and to the Km. Okay. So this one's very easy to identify on a Lineweaver-Burke plot, parallel lines. This means that the inhibitor is binding the enzyme substrate complex. So this binds at an allosteric site. Allosteric away from the active site. Then that's because the active site's already full of the substrate, so this must bind somewhere else. Additionally, if we increase the concentration of substrate here, it has no effect on getting rid of this inhibitor. I'm going to back up for a second, because I forgot to mention that. So for the competitive inhibition, if we increase the amount of substrate well beyond the inhibitor, this can still go forward. Okay? So, a competitive inhibitor that you may have heard of is carbon monoxide. So that's the formula CO. It looks like O2. So this binds the hemes in your blood, the hemoglobin, and this is why you have carbon monoxide detectors in your home. The way that you get rid of carbon monoxide is the ambulance will come and give you an oxygen mask, because the oxygen will then outcompete the inhibitor and take over all of the active sites if we supersaturate all of the enzymes with oxygen. We can't do that with uncompetitive inhibitors. And that's because the uncompetitive inhibitors are not binding the active site. They are binding a site away from the active site, so we can't do the same things here. Okay. So the final one we want to talk about is mixed inhibition. So a mixed inhibitor, a mixed inhibitor can bind either the enzyme or the enzyme substrate complex. Oops. Don't mind my terrible handwriting. Enzyme plus product. So the inhibitor can bind here to make our EI plus S, or it can bind the enzyme substrate complex as well. So you can imagine that this doesn't look anything like the substrate, EIS. Okay. In your book it ignores this. Sometimes this happens, that the substrate can bind while the inhibitor's bound. But your book ignores it. That's okay. So the point here is that this is mixed because it can bind the empty enzyme or the enzyme substrate complex. Completely bizarre, and that's why it's mixed. It does both. It does both competitive, non-competitive sort of deals. So as you can imagine, this affects K1, this affects K-1, and this affects K-cat. And what ends up happening in mixed inhibition is that we get a point somewhere over here where these two lines cross. And just like we saw in competitive and uncompetitive, I'm trying to draw this straight, when we add the inhibitor, this line shifts upward. But the intercept is not at the Vmax position as it is for competitive inhibitors, nor is this parallel as we see in uncompetitive. Okay, so each of these three plots are unique, and I expect you to know them for the exam. Okay, so this ends up increasing the Km, which is not good, and this also decreases the Vmax, which is also not good. And just like uncompetitive, if we add more substrate, that doesn't make our inhibitor problem go away. We have to do something else in order to prevent the inhibition.